Given recent developments in the rekindled ambitions of particle physicists, the grand game of understanding the nature of the cosmos has therefore started, and revolution is about to break out. Scientists at the European Centre for Nuclear Research, or CERN, have restarted their cosmic gun, a large Hadron Collider. Before it underwent its repair, the collider had already been producing evidence that the universe may be hiding something remarkable. Join us as we investigate how scientists at CERN have just unearthed an astonishing discovery that alters everything. What is the genesis of the cosmos, and why does it contain matter as opposed to antimatter? When scientists discovered the Higgs boson, a long sought after particle that gives the rest of the cosmos its mass but is still missing practically everything, with it, several physicists made headlines throughout the world a decade ago. When the Sun Collider was turned on for the first time in 2010, optimist physicists claimed that the cosmos was up for grabs and that the Higgs boson was its intended target. This particle serves as the foundation for the Standard Model, a set of equations that explains everything scientists have been able to measure about the subatomic realm. However, the Standard Model is unable to explain some more fundamental aspects of the universe, such as its origin, the elements that make up the universe, and even why the Higgs particle itself has mass. Recent findings may help to clarify some of the riddles surrounding dark matter and other things. Scientists are positive about it since they can detect the gravitational signals of dark matter. This dark matter constitutes the majority of the universe, but scientists have yet to determine what it is made of. The most important thing scientists know about dark matter is that it is responsible for the universe's expansion. It is so enigmatic that measuring it is difficult, if not impossible. According to NASA, known matter, such as what humans are made of, accounts for less than 5% of measurable matter. Astronomers have deduced that the universe is densely packed with dark matter, a substance that cannot be directly observed but whose powerful gravitational pull keeps galaxies from colliding. According to the most recent research, dark matter outweighs visible matter by a factor of 5. Despite this, dozens of intensive searches by astronomers around the world have failed to identify the composition of dark matter. Dark matter has been difficult to locate because it is hidden in the mirror world. It is a stunning realization that most matter in the universe is genuinely invisible to us. This is one of science's open-ended questions. When the big collider was turned on for the first time in 2010, physicists thought that some answers might emerge, but aside from the Higgs, nothing else was discovered, especially no novel particle that would shed light on the mystery of dark matter. Astronomers assume that it must exist because the invisible cosmic framework known as dark matter is what holds galaxies and galaxy clusters together. We don't know exactly what it is, though dark matter is for sure one of the most intriguing scientific puzzles. Unfortunately, the Standard Model was unaffected when the collider shut down at the end of 2018 for significant maintenance and enhancements. After 2025, the collider will shut down for an additional 2 years to allow for the installation of other substantial improvements. This series of renovations also included changes to the massive detectors that sit at each of the 4 locations where the photon beams collide and study the collision debris. These detectors have been tested since July. Squeezing the proton beams makes protons more likely to collide at the points of intersection. But it also confuses computers and detectors since there are several sprays of particles that need to be distinguished from one another. Since then, a number of investigations have shown holes in the mainstream model and called for a more thorough examination of the cosmos. These discoveries deal with peculiar behavior of subatomic particles, whose names are mostly unknown to us in the cosmic realm. Think of the Muon as a subatomic particle that briefly rose to stardom in 2017. Muons, which are 207 times more massive than electrons yet have the same negative electrical charge, are frequently referred to as fat electrons. Muons are formed during collider events and by cosmic ray collisions, and they decay radioactively into a burst of electrons and spectrum neutrinos in just a few microseconds. Nobody is quite clear how muons fit into the whole picture. Muons spinning in a magnetic field wobbled significantly more fast than the Standard Model predicted, according to 200 physicists from the Fermi National Accelerator Laboratory in Illinois. This finding was revealed last year. The value of a parameter called G2, which described how a particle reacts to a magnetic field at the 8th decimal place, revealed the quantum whisper of as yet unidentified particles that would momentarily form around the muon and alter its properties. This difference between experimental results and theoretical expectations. In order to study nature at the smallest scales, it was believed by scientists to be the reason for the minor but considerable deviation, since the standard model would finally be broken. The Higgs boson has access to extremely high energy scales, making it both a powerful telescope and a very fine microscope. Physics, because it seeks to decay to a truer vacuum with a lower energy, a vacuum is referred to as a false vacuum by physicists. Our universe is kept in this fictitious vacuum by the Higgs field's energy potential's dips and hills long enough for planets, stars, and galaxies to form. However, this fictitious vacuum is inherently unstable and will degrade over time. Quantum energy fluctuations, or the strange quantum tunneling phenomenon, may be able to help the fake vacuum break through the energy barrier, allowing it to cross those hills and roll down the slope on the other side. Since only the Higgs field is preventing vacuum decay, we should be grateful for the existing cosmos. If the fake vacuum disintegrated, everything would be obliterated and replaced with a true vacuum, which would spread outward in a wave traveling at the speed of light. These models are crucial to the Hadron Collider's quest to discover physics that goes beyond the standard model. So here is yet another attempt to comprehend the world. Despite its many accomplishments, the standard model of particle physics is by no means the final word on the subject. For instance, it does not fit cosmological models that explain the origin of the universe. However, while they wait for more information from the Fermilab experiment, two groups of theorists are still trying to match up their predictions of what G2 should be. Another oddity involves the muon, one of the 6 types of quarks that make up heavier particles like protons and neutrons. Theorists are currently attempting to match up their predictions of what G2 should be. The 2-quark B meson particle contains the B quark, which is the protagonist or antagonist of this tale. However, due to their instability and inclination to dissolve, these quarks appear to defy the standard model. According to the standard model, some unusual decays of a B quark may include a daisy chain of events that produces a new, lighter quark and 2 light particles known as leptons, which could be electrons or their fat relatives muons, or both. It is equally likely that electrons and muons will show up in this process. Dr. Patel and his associates have detected more electron couples than muon pairings, contradicting the Lepton universality principle, despite the tau being a third heavier lepton but decaying too quickly to be seen. If these findings hold up in the future collider run, Dr. Patel believes that a subatomic particle known as a leptoquark would be one of the most dramatic possibilities. This aberration, like the muon's magnetic anomaly, points to an unknown influencer, a particle of force interfering with the reaction. If the particle is real, it might bridge the gap between the heavier leptons, such as electrons, muons, and neutrinos, and the quark-based protons and neutrons that make up the material world. Temptingly, there are 6 different quark kinds and 6 different lepton types. Dr. Patel said we are entering this run with more optimism that there may be a revolution coming. The W boson, which carries the so-called weak force responsible for radioactive decay, is another particle in this menagerie acting strangely. The Collider Detector at Fermilab, or CDF, reported on a 10-year effort to measure the mass of this particle in May. The effort was based on roughly 4 million W bosons collected from collisions in Fermilab's TeV. The W boson should weigh about 80 billion electron volts, which was the most powerful collision in the world before the massive Hadron Collider was built, the best way to quantify mass energy based on past mass measurements and the standard model. In contrast, the Higgs boson has a mass of 125 billion electron volts. The WCDF measurement, the most exact measurement ever, came in at 80.433 billion, which was greater than expected based on the experimenter's 7 sigma calculation, where the possibility of an error was only 1 in 2 trillion. This deviation was a statistical anomaly. If this latest disparity holds up, the standard model may still have another weakness, since the mass of the W boson is related to the masses of other particles, including the infamous Higgs. With more knowledge, the three anomalies may all appear, as well as the revolutionaries hope, yet all three identify unknown forces or particles that interfere with existing physics. Kyle Cranmer, a physicist at the University of Wisconsin who participates in other CERN projects, stated that a new particle that would explain both G2 and the W mass might be discovered at the LHC, which is encouraging to optimists as a result. The LHC will be used by researchers to examine the Higgs particle's more delicate interactions and search for evidence of the elusive dark matter, which makes up roughly 27% of the universe's matter but has never been directly observed. Hence, even though the LHC won't tear the fabric of time and space, it might help researchers lift the curtain on some of the universe's mysteries. Whenever they will uncover more mysteries, we will make sure to keep you updated on them too. That pretty much wraps this video up, guys. Thanks for watching. Let us know of your opinions in the comment section below. Remember, be sure to subscribe to this channel with the bell notification if you enjoy watching our content. We upload some pretty awesome stuff here, which you will most certainly enjoy. Hit a like on this video and leave a comment below. See you guys in the next one.